Finding roots allows us to understand the behavior of complex systems, from physics trajectories to economic trends. Identifying where a function equals 0 is the most critical step in analyzing any higher-degree polynomial expression. The rational root theorem provides our starting point. By dividing the factors of the constant term by the factors of the leading coefficient, we create a finite list of potential rational candidates to test using synthetic division. Synthetic division is a shorthand method for polynomial division. We strip away the variables and work only with the coefficients. We will start by testing x equals 1, which is often the easiest candidate to evaluate first. Bring down the 2, multiply by the root 1, and add it to the next coefficient. Repeat this process until you reach the end. Since our final result is 0, we have confirmed that x, 1, is a factor. A remainder of 0 is our green light. It proves that the value we tested is a true root. The numbers remaining below the line represent the coefficients of a new polynomial that is 1 degree lower than our original. Now we repeat the process for our new quadratic. While we could use the quadratic formula, let's test a fractional root like 1/2 to see how synthetic division handles non-integers efficiently and accurately. Even with fractions, the steps remain the same. Half of 2 is 1, adding that to 5 gives us 6. Half of 6 is 3, which cancels out the -3. We have successfully found our second root at x equals 1/2. When a root is a fraction like 1/2, we convert it into a linear factor with integer coefficients. Multiplying the equation by the denominator ensures our final factored form is clean and easy to work with. The last remaining part is 2x plus 6. By factoring out a 2, we find our final root at x equals -3. We have now successfully decomposed the original cubic polynomial into 3 distinct linear components. Graphing tools are excellent for verifying our work. By plotting the function, we can visually confirm that the curve crosses the x-axis exactly at the values we calculated, -3, 1/2, and +1. Let's try one more example. For this polynomial, our rational root theorem suggests several candidates. We will begin by testing -1 to see if we can reduce the degree of the equation. After dividing by the factor, x plus 1, we are left with a quadratic. Reducing the degree step by step is the core strategy for solving any higher degree polynomial, regardless of how many terms it has. We factor the remaining quadratic to find the final 2 roots. Our complete set of solutions includes an integer, a negative integer, and a fraction, demonstrating the variety of roots a single polynomial can possess. A common mistake in synthetic division is forgetting to include a 0 for missing powers of x. Always write your polynomial in descending order and use a 0 placeholder to keep your columns aligned. To summarize, use the rational root theorem to find candidates, apply synthetic division to test them, and use the resulting quotients to find the remaining roots until the polynomial is fully factored. Try this one on your own. Use the root x equals -2 as your starting point for synthetic division. You should find that the polynomial factors neatly into these 3 linear terms. How did you do? You now have the tools to tackle higher degree polynomials with confidence. By combining the rational root theorem with synthetic division, no root is out of reach. Thank you for learning with us. Generated by Vision Solve AI.